We discussed the k-mer index as well as two different multi-map data structures that we can use to implement the k-mer index. And now we'll see two variations on the theme of a k-mer index. So before, when we built our k-mer index, we built it from all of the k-mers from the text T. Every k-mer offset pair appears in this index, for example. And it starts with the 5-mer at offset 0 and goes all the way to the 5-mer at offset 6. So, but what if we didn't take every k-mer? What if instead we took every other k-mer? So for example, what if we took just the k-mers that are at even offsets with respect to the text T, and we got rid of the k-mers that were at odd offsets with respect to the text? So for example, starting with the index you see here, we can remove, as you see indicated by these red slashes, we can remove the k-mers that start at the odd offsets. And so once we remove them, we're left only with the k-mers that start at even offsets. So why might we do this? An advantage is that the index is now smaller, right? The index takes up less memory. And it's also a little faster to query. So for example, if we were using binary search to query this index, we've now cut the size of the index in half, which is going to save us about 1 bisection when we do binary search. So it's going to be a little bit quicker to query. On the other hand, the fact that there are fewer k-mers in the index now might be a little bit concerning. So you might wonder if that'll cause us to miss some of the matches that we might otherwise have been able to find if we had kept all the k-mers in our index. So for example, say we are trying to match this pattern P that you see here, and we take the first 5-mer from P and we query the index, but we don't get a hit. This particular 5-mer does not appear in the index, and yet this pattern P does occur in the text T. You can see it occurs right here, GCGT, GCTT. So that's concerning. But you might also notice that if we had just taken, instead of the first 5-mer, if we'd taken the second 5-mer from P and used it to query the index, we actually would have found 2 hits. And these correspond to these 2 different offsets with respect to T. And if we do verification at these 2 offsets, we'll find that in the case of the second offset, there was in fact a match. So we'll find the match. If we used just the first k-mer, we would have missed the match. But if we tried both the first and the second k-mer, then we would have found the match. So let's think about this scenario again, but using a slightly different picture here. So here we represent the text T here up at the top. And the k-mers that we add to the index are shown here below. And then here's our pattern P. And then the k-mers that we take from P in order to query the index are shown here. So again, our strategy is to build the index with every other k-mer from the text, every even offset k-mer. So here's the k-mer at offset 0, the k-mer at offset 2, offset 4, offset 6, etc. And then we query the index using the first k-mer from P here, recording all the index hits that we find, and then we query it again using the k-mer at the second offset with respect to P here. And again, we record all the index hits that we find, and we verify all those hits. So actually, there's nothing all that special about using the first and second k-mers from P. So the important thing is that the 2 queries have to come from even and odd offsets with respect to P. So in the example we just saw, we used the k-mers at offsets 0 and 1 with respect to P. But in another scenario, we might have used different k-mers. So here are the k-mers at offsets 4 and 3 with respect to P. That's fine, as long as one of them comes from an even offset and the other one comes from an odd offset with respect to P. And in fact, it's not too hard to generalize this scheme so that we index not every other k-mer from the text T, but say every 3rd k-mer, or every 4th k-mer, or every nth k-mer where we can choose that n. So for example, say that our index is built not over every other k-mer, but over every 3rd k-mer. So maybe that looks a little bit like this. Now given, so here we are, we've extracted the 0th and the 3rd and the 6th, the k-mers at all the different offsets at multiples of 3. And then we query it 3 times now instead of twice. We query it with the first 3 k-mers with respect to p. Right? So similar thing, but we're doing it in taking every third instead of every other. And then again, there's nothing special about taking the first 3 k-mers with respect to the pattern p and using those to query the index. We could have just picked any 3 as long as they are at different offsets modulo 3. You know, using modular arithmetic, where some offset modulo 3 is just the remainder after dividing by 3. At any rate, it's easy to generalize this scheme so that instead of taking every other k-mer, we take every nth k-mer. So moving on to another variation on the theme of a k-mer index. Instead of building the index over substrings taken from the text T, we can also build the index over subsequences taken from the text T. So what's a subsequence? How is that different from a substring? Well, a subsequence of a string S is a string consisting of characters that also occur in S in the same order, but not necessarily all in a row, not necessarily consecutively, which was a requirement of a substring. So for example, here's a string, this string called seek here. And here is a subsequence of that string. And the way we got this subsequence is that it consists of the character at offset 0, concatenated with the character at offset 1, concatenated with the character at offset 5, offset 7, and it makes this subsequence here. So AAGT is a subsequence of the string, but it is not a substring, right? We can look for it using .find, and we get the return value -1, which just basically means that does not occur as a substring. So that string does not occur as a substring, but it is a subsequence. So substrings are always also subsequences, but subsequences are not necessarily substrings. In order to be a substring, there has to be some place where those characters occur consecutively in a row in the string. So let's look at an example of this. So here, instead of taking the first 5-mer of T and putting it into the index, we're going to take the first subsequence of a particular shape. So the shape of the subsequence is indicated by the blue underscores here. So we're going to take 2 characters and then skip 1, and then take 1 character and then skip 1, and then take 2 more characters after that. So we're going to take all these characters and concatenate them together and then insert them into the index. And here we go. We get this subsequence extracted from offset 0. And then we can do the same thing at offset 1. Again, we take a subsequence. It's of the same shape. So we'll take 2 characters and then skip 1, and then take 1 character and then skip 1 and then take 2. And then we'll insert the corresponding entry into our index. And we do the same for offset 2, and we do the same for all the other offsets. And here is the index we would get if we did things this way. So now we have an index built from subsequences of T, and if we have a pattern P, and we would like to now query this index, then the first thing we would do is we would extract the same shaped subsequence from the string P. So in this case, again, we'll take the first 2 characters, GC, and then skip 1, and then take the next character, and then skip 1, and then take the next 2. And those concatenated together are going to be our key that we can go look up in the index. And in this case, we will look in the index and get a hit at offset 3. So why should we do this, and what sort of advantages and disadvantages would it have? Well, the short answer is that it tends to increase the specificity of the filter provided by the index. In other words, when we get an index hit, it's going to lead to a successful verification more of the time than if we had taken those characters to be consecutive, to be a substring of T. And we'll elaborate on what this means a little bit later in a homework assignment.